Dear students, in previous lecture we discussed exponential function, and you know that exponential function defined by b of x, where b is greater than 1, it is 1 onto function, means it is invertible function. Now when it is invertible function, this means that its inverse exists from or positive to or. So if we consider a function f from or positive to or, where or positive is set of non-negative numbers, that is positive real numbers. Let b is greater than 1, means fixed number which is positive. Then if we define f of x equals to log of x with base b, if b raised to power x equals to f of x, then this function is called as the logarithmic or the log function. Actually, this function is the inverse of the exponential function. You know that the exponential function is a function from g r to r positive defined by g of x equals to b of x. Here we are considering base b in this log function, so we have to consider b as the base in the exponential function also. Now we have to prove that these two functions are invertible. In order to prove are inverses to each other, in order to prove this, we will simply show that fog as well as golf is identity function. Now g of x is simply g of f of x. Now f of x is here defined as log of x, that is log of x to the base b. Now g of x is simply b raised to power x, it is simply b raised to power log b x, log b x. Here base and this is common both for these logs, so it is simply x. Similarly, f of g is fog, it is f of g of x. Now g of x is defined by b of x. Now f of x is defined as log of x, which implies that f of b of x is log of b of x, which is simply log of b raised to power x upon x, which is simply x, because log of b with base b is 1. Hence b of x, that is exponential function, and log of v of x are the inverses of or inverses to each other. Now this is one way to define log function through using concept of bijectivity. Now if we have this, we have second definition as, if b is positive number, then we can say logarithm of a to the base b is x. If b raised to power x is a, if b raised to power x is a, that is log of a to the base b, because b is here, base is x. Like if we have 3 raised to power 2 is 9, which implies that log of 9 to the base, here base is 3 to the base 3 is 2. So simply we can say that it gives us about it gives us idea about the indices or exponents or degrees of a positive base which are greater than 1, because here log of this 9 with base b is 2, so 2 is here index, or 2 is here power for this. So simply it gives us idea about the indices or simply the exponents of a positive bases which are simply greater than 1. You know that if base is 10 in exponential function, it is called as the common exponential function. Similarly in this, if base is 10, that is if b is 10, it is called as the common log. While if base is e, it is called as the natural log, and this natural log is simply denoted by ln, capital Ln. That is this log with base equals to e, where e is a rational number whose value lies between 2 and 3. You know that the algebra of logs as log of b, that is log of xy with base b, is log of x plus log of y. Log of x raised to y is simply y log x with base b, and log of x upon y is log of x minus log of y. You know this. Now how to change the base, that is base change formula. Now if we have a log of x is alpha with base a, log of x is beta with base b, and log of a with base b is gamma. Now here log of x is alpha, which implies that base is here a raised to power alpha is x. Here b raised to power beta is x and b raised to power gamma is a. Now here x equals to x, which implies that a raised to power alpha equals to b raised to power beta. But here a is b raised to power gamma, which implies that in put here a raised to power this a as b raised to power gamma, it is simply b raised to power alpha into gamma equals to b raised to power beta, which implies that because bases are same here for these two sides, and b is greater than 1, which implies that alpha into gamma equals to beta. But alpha is here log of x with base a, gamma is here log of a with base b, and beta is here log of x to the base b, which implies that log of a of x is simply log of b of x upon log of b upon a. So in this way, if we have to change b into a, then log of a of x is simply log of x upon b upon log of a upon with base b. So this is the rule how to change the bases from one positive number to second. Now if we want to convert this natural log and this common log into the natural log, that is common log is here log of 10 to the base, simply log of x with base 10. Now if we want to convert this into the natural log, it is simply log of e of x, log of x with base e upon log of 10 with base e. So this is the rule to change the base for any function. Now some features of this logarithmic function. Log is not defined for the natural numbers because that its domain is all positive. That is also since b is greater than 1, b raised to power minus infinity is simply, if we have this b raised to power infinity, it is 1 upon b raised to power infinity, which is 1 upon infinity, that is 0, which implies that b raised to power minus infinity is this 0. Hence log of 0 with base b is minus infinity. So this approaches from this side, from 0 side, this function approaches to minus infinity. Also log of b with base b, a base and this is same, which implies that it is always 1 because b raised to power 1 is always b. Similarly log of infinity is infinity. So if we want to draw this graph of this log function, it is domain is from this positive to infinity, and at 1 it is 1, at 1 it is 0 because b raised to power 0 is always 1, which implies that log of 1 with base b is always 0. So it is the required graph for this, from this to this. Clearly it is from the graph, it is 1 1 on to from or positive to or. That if we have this exponential function, natural exponential function, and natural log, that is log of x with base e and e raised to power x, then this is the graph of e raised to power x, and this is the graph for this log function, that is natural log. Because for any with any base, this log always touches x-axis at x equals to 1, because b raised to power or any number raised to power 0 is always 1. Here if we draw this axis, if we draw a line passing through this origin as y equals to x, then clearly these two graphs, this graph of this e raised to power x and graph of log of e of x, these are mirror images through this y equals to x. When we have two graphs which are mirror images of each other, that is through y equals to x, then we say that these are the inverses to each other. Clearly this is another way to check whether the two graphs are inverses to each other or not. Draw a line through through origin as y equals to x. If these two graphs are the mirror images, then you can say that these two are the graphs of two functions which are actually the inverses to each other. Now if we have x raised to x equals to e raised to power log x, x equals to e raised to power log x, we have to prove that this is true. Is this true for all x? Since that log is defined for all x belongs to 0 infinity. Now if x belongs to minus infinity 0, that is negative numbers, this log is not defined. Now if x is greater than 0, then we can have log x equals to, taking logs on both sides, log of x equals to log of e with raised power log x with base here e. It is understood here that base is here e. It is log of a x xy. So it is xy log x, that is log x into log e, which implies that log e is 1. It is log x log x, or x equals to x, which implies that x equals to e log x, because this is true. Hence x equals to e log x is true for each and every value of this 0 infinity, because domain for this is positive numbers. Here you can also prove that differentiation, or you know that the differentiation, that is d by dx of exponential function, is e of x, while as d by dx of log x is 1 by x. 1 by x. So inshallah in tomorrow's lecture we will discuss, you know, this logarithmic differentiation or exponential differentiation. So thank you.